Chem 106, Chapter 16, Lecture 4. The next two sections of the chapter outline on acid-base titrations and on pH indicators are covered in laboratory experiments, and they are not going to be on the exam and lecture, so we will not talk about them here. The last topic to be discussed in class for this is the solubility of salts. The solubility product constant, which we then designate as K sub SP for solubility product, is the value of the equilibrium constant that reflects the solubility of a compound. Now, in context, we're going to limit the discussion to what we call insoluble salts. And to say insoluble sounds silly, because if it's insoluble, then it's not soluble in water, so how could there be any solubility? But when we say insoluble, what it means is that it falls below the threshold of the definition of solubility. So that to a very small extent, insoluble salts still have solubility in water. They just don't meet the definition of soluble. I know that still sounds silly. But so we will say limited solubility salts then. But you will hear it called insoluble salts. But understand that we're talking about limited solubility. And so what we can do then is if we write an equation that expresses the solid salt dissociating into solution, and in order to measure this, you must have a saturated solution. So what you're going to do is you're going to have some fixed amount of water, and you're going to put the salt into the water and ensure that you have solid residue on the bottom of the container so that it ensures that the solution above is saturated with the ions of that salt. So what you can do is you can put the salt in the water, stir it around for a while, let it set for half an hour or so until it reaches equilibrium. Then what you find is that this solid salt on the bottom of the water mixture is in equilibrium with the ions in solution above it. And so when we write a K expression for this, what you're going to see is the only parts that go into the expression are the aqueous and not the solid. So the KSP is going to be equal to the concentration of the cation A times the concentration of the anion B raised to their molar coefficients from the dissociation. And so when we say this, we talk about the solubility. It shouldn't be confused with the solubility product constant. Remember, the solubility product constant, just like every other K, is only an estimation of how far away from the equilibrium it really is, or where the equilibrium lies. In other words, is it reactant favored, product favored, that kind of thing. So when we talk about solubility, by definition, solubility is the quantity present in some volume of saturated solution. And usually when we say soluble, a salt that is soluble dissolves at least 3% or greater in some quantity of solution. But we're talking about limited solubility here. And so our solubility product constant values are going to be rather small because the equilibrium lies very far to the left, which means we should have Ks that are significantly less than 1. All right, so how do we calculate this then? We have lecture problems that we can do this, but just know then that relating solubility and KSP, the solubility products are determined by very careful laboratory measurements with equipment that we can't even imagine in our labs. And we can use the KSP just as a general estimate of the solubility of some salts. So if we know the KSP, and if it's really low, the lower the smaller the KSP value, the more insoluble the salt is. So we can just relate them that way. We're not defining how soluble it is. We just relate the idea that the smaller the KSP, the less soluble that salt is in water. Let's see. And the relative solubilities often can be deduced by comparing values of solubility product constants. And so how soluble one salt is to another is what they mean. And so direct comparisons of the solubility of two salts can only be done if they have the same cation to anion ratio. But none of this helps you solve problems for the exam. So let's go ahead and do some lecture problems. we're going to do problems 11, 12, and 13. And so if we look at number 11, it says that the solubility of lead 2 iodide in water is 0.54 grams in 1 liter of water at 25 degrees Celsius. What is the value of KSP for lead 2 iodide? And they give you the molar mass of lead 2 iodide being 461 grams per mole. All right, so when we look at this then, the first thing we want to write is a dissociation equation. When lead 2 iodide is put into water, what does it do? All right, so lead 2 iodide, solid, is going to go into equilibrium with the solution above it to produce lead 2 aqueous plus 2. Remember, this subscript has to then go out in front to become a coefficient. So 2I minus aqueous. And by now you should be good at writing these. Whenever you see it, you should be able to write it out as a dissociation. Alright, so now we have this. So the KSP is going to be equal to the concentration of lead in solution times the concentration of iodide in solution squared. All right. Now we need numbers to fill in there if we're going to solve this. And so we were told that 0.54 grams of the lead 2 iodide dissolves into 1 liter. And so in order to figure out moles, because we can't do anything without that, 0.54 grams divided by the molar mass, mass over molar mass, gives you 0.001171367 moles. Now, again, we were given also in there that it is in 1 liter of solution. And let's check the significant digits on that just to be sure. Yes, 1.0 liter of solution. That means then that the concentration of the lead 2 iodide is 0.001171367 molar at 25 degrees Celsius. Okay, so now in order to calculate this, we have to make some logical connections with this. What this represents is the concentration of the lead 2 iodide, but you need to understand then that the relationship of this, we say this is 1, the solubility, so we're dissociating. The lead 2 plus to the lead 2 iodide is 1, but notice here that the relationship of the iodide to the lead 2 iodide is 2 to 1. So whenever we plug these values in, you have to remember to take that into account. And so what we have then is the KSP is going to be equal to the concentration of the lead, which is the same as the lead 2 iodide. That's going to be 0.001171367 times, now there's 2 iodides, so you have to multiply that by 2 to take into account that there are 2 iodides for every 1 lead 2 iodide that dissociates. And you have to square it, because that's part of the expression. So not only do you have to double it, you have to square it. So you have to remember to do both of those things. And had this been a sub 3, then you would have to multiply it by 3 and cube it as well. So whatever the subscript is, that's going to end up being both multiplicative as well as raised to its exponent for that species. Very, very, very important to remember to do so. And so what we end up with then is 0.001171367 times 0.002342733 squared equals 0.001171367 times that squared value, which is 5.4883 3,98794 times 10 to the minus 6th, which, again now gives us a raw answer of 6.428929,230 times 10 to the minus 9th. So now, of course, as always, we have to do the rounding at the end. And we started with 2 significant digits there, so we better end. There was no log to worry about or anything, and it was all multiplication division. So 2 significant digits gives us 2 significant digits in our answer. So our final answer for this is 6.4 times 10 to the minus 9th. And that is the solubility product constant for lead-2 iodide in water. All right, so now we can also then, instead of calculating the KSP, we can calculate a concept known as molar solubility then, using a known KSP. So clear this out, and we look at problem number 12. They ask you to calculate the molar solubility of lanthanum 3-fluoride in pure water at 25 degrees Celsius, knowing that the solubility product constant for this substance is 2.0 times 10 to the minus 19th. All right, so again, start at the beginning with this stuff, and you write a dissociation equation. Lanthanum 3-fluoride, solid, is going to dissociate to form lanthanum 3 plus aqueous plus 3-fluoride aqueous. Okay, so now we need a KSP expression. KSP, hold on, okay. KSP is going to be equal to the concentration of lanthanum times the concentration of fluoride raised to the 3rd power. All right, so now in this case we know that the KSP is 2.0 times 10 to the minus 19th, but we don't have any other data to get the concentrations of the ions. Well, here's where we invoke algebra again. Since we don't know, and by the way, let's redo our relationships here, that the lanthanum 3-fluoride is taken to be 1 because that's the formula of the salt itself. The lanthanum is 1-to-1 with that lanthanum 3-fluoride, but the fluoride is 3-to-1. So make sure you remember this in the calculation. And so we go back to algebra. The lanthanum is just going to be X because we don't know, any numbers associated with it, but it's 1-to-1 with the salt, so it's just X. But the interesting thing is then the fluoride is 3-to-1, so that's going to be 3X, and because that coefficient of 3 is out there, we have the exponent of 3. So remember, again, you have to take your subscript, you have to multiply it inside the parentheses as well as raise it to the exponent. And so what you end up with then algebraically is you have X times the quantity 3X cubed, which gives you 27X cubed, times X gives you 27X to the 4th. So make sure you understand this math as I'm doing it. And as always, if you're not sure, come see me or send me email and I'll do my best to explain. But you just follow the math logically through. Just make those algebraic connections and follow it through. And so what we end up with is this then. So we in the end have 2.0 times 10 to the minus 19th equals 27x to the 4th, where x is going to end up being our solubility number. All right, and so when we look at this then, we start doing the arithmetic on it. What we find is then we have to divide both sides by 27 to get rid of that. And when you do, you end up with, oops, my apologies. Start that again there. What you end up with is 7.407, and that 407 repeats, so I'm going to put a line over it, times 10 to the minus 21 equals x to the 4th. Now, in order to solve this, you have to be able to use your calculator appropriately. So you should have on your calculator an x to the y, or better yet, if you had a button on there that had a root x to the root y, x to the root y. So if you can find these buttons, then that's to your best interest. What we're going to do is we're going to have y, in this case, being a 4, but here it's going to have to be to the 1/4. So if you have an x to the y and you don't have an x root to the y, then you're going to have to use this a little more creatively. And so what that becomes is the x to the y button, because we're trying to take the 4th root, it becomes x to the 1/4, the reciprocal of 4. All right, and so either way, you figure out your calculator and you figure out how to get that 4th root. What you're going to find is that x then itself is going to be equal to 9.277192279 times 10 to the minus 6th. And again, you have to remember in this context, we solved for a concentration, so you have to remember to put molar on the end of it. It will be wrong if you don't put it there. And then, of course, the very last step, as always, is we have to round. And so our k value gives us our constant here. And that had 2 significant digits in it, because remember, these are all measured. So that's the only number we were given. So we have 2 significant digits, so our answer must have 2 significant digits. The 7 modifies the 2, so this becomes, this becomes 9.3 times 10 to the minus 6th molar. All right. Now, an interesting thing, and you can look at this on the last page of your chapter outline, is what happens if we decide to add a common ion to the mixture. And that's what number 13 is all about. So we know that the molar solubility in pure water for this is 9.3 times 10 to the minus 6 molar. But what if we add a common ion? The result will always be that the molar solubility decreases. So when you have a molar solubility of the pure substance in water, that gives you some value. But if you add a significant amount of a common ion, either the cation or the anion, if you add a significant amount of that to the solution, the molar solubility of that substance decreases significantly. This is one way we can do wastewater treatment. Like, let's say if we were doing something industrially that involved mercury, then what we could do is in the wastewater stream, before you send it out down the drain, whatever, what you can do is then you could say if you had, let's say mercury sulfate, just as an example, then what you could do is in the wastewater stream is you could add a whole bunch of potassium sulfate, which isn't harmful, but you could add a whole bunch of the potassium sulfate. That acts as common ion sulfate. Remember, it was mercury sulfate? And now we add in a whole bunch more potassium sulfate. The potassium doesn't matter, but the sulfate does. By Le Chatelier's principle, that's going to force it backwards to the left and therefore make the mercury even less soluble. So we can precipitate out essentially all of the mercury into a solid form, put it into what we call a lab pack, send it off for landfill, and that way it's not in the water anymore. So these solubilities really have a practical application, and the idea of using a common ion effect to lower the molar solubility has its true applications, especially in the environmental area. All right, but let's look at 13 then, where we still then, because we know from 12 we had the molar solubility of the lanthanum 3 fluoride. So let's do a comparison to show how that molar solubility decreases. So once again, our equation is going to be the lanthanum 3 fluoride solid goes into equilibrium with the lanthanum 3 plus aqueous plus 3 fluoride aqueous. But now in this case, what we're going to do is let's put in also 0.010 molar fluoride from whatever source. We don't care where it came from. Could have been sodium, potassium, lithium, whatever. But let's just say that we dumped in 0.010 molar fluoride as well. What is the new molar solubility of the lanthanum fluoride? And this is still nothing more than a little bit of algebra, right? Because again, KSP is going to be equal to the lanthanum times the fluoride raised to the third power. But now we have the addition of this 0.01 molar fluoride. Oh no. No, still follow logic. The lanthanum fluoride serves as your 1, and the lanthanum is 1 to 1, but we don't have any numbers because we're going to pretend like we don't know that part from 12. And so we call it X. The fluoride now, of course, it has the 0.010 molar in the beginning also, right? Plus, because it got added in, plus its original 3x all cubed. Now this looks like it's going to make a very terrible equation to solve, doesn't it? But it doesn't have to. Because remember, you can't just like cube the 0.01 and then cube the 3x. That's not how that works. You'd have to have 3 separate terms of 0.01 plus 3x times 0.01 plus 3x times 0.01 plus 3x to do the algebra. And that could get really, really messy in terms of exponents. But fortunately, we learned in this chapter earlier on a new rule to help us see whether we really need to play with that or not. And so let's plug some numbers in to help us make sense of this. So we know the KSP is 2.0 times 10 to the minus 19th. And that's going to equal the x times the, and actually I'm going to rewrite that in scientific notation just to make it clearer, that becomes 1.0 times 10 to the minus 2 plus 3x cubed. And let's analyze that directly. When I look at this minus 2 and this minus 19, are they at least an absolute difference of 10 to the 2? Different? I would say they are. Minus 2 and minus 19 are 17 magnitudes of order different than each other, which meets that criteria, which says then we don't have to worry about the plus 3x. So all of a sudden, our equation becomes 2.0 times 10 to the minus 19th equals x times 0.010 cubed. Because we can forget about the plus x now. Because that plus x is so negligible compared to that 0.01 molar fluoride that was dumped in that the plus 3x doesn't contribute enough to make it worth all the algebra. It's going to drop off significantly anyway. And if you're just that kind of personality, you certainly are free to go ahead and do the calculation the long way and see that it never changed the answer anyway. It will not change your answer. So this is our test that lets us get rid of that. And so now we are to this small expression. All right, and so that's going to be equal to the x, and then 0.01 times or cubed is going to be 1.0 times 10 to the minus 6. So now divide both sides by 1.0 times 10 to the minus 6th. And this is going to give you x equals, I want to be sure here, 2 times 2.0 times 10 to the minus 13th. And again, we're talking about molarities. These x values in there are molarities. Do not forget, remember to put your molarity on the end there. And now, significant digits-wise, that's what we started with, so of course that's what we're going to end with, is we had 2 there and 2 there, so of course we end up with 2 here. And so, notice now that this molarity is 2 times 10 to the minus 13th, whereas before, when we calculated it as pure substance, it was 10 to the minus 6th. So it's dropped 7 orders of magnitude, and this is different for every salt. Don't think this is the same. But for every salt, it's going to be unique. But in this case, simply by the addition of 0.01 molar fluoride, you've dropped the solubility, the molar solubility of the lanthanum 3 fluoride by about almost 7 orders of magnitude. That's very significant. And like I said, this has potential use, say, in the environmental field when we want to clean things up. All right, let's check the outline just to be sure where we're at here. And so the common ion effect, again, the main thing here is that the solubility of the salt is reduced by the presence of a common ion. We saw in the case of lanthanum 3-fluoride, it dropped by nearly 7 magnitudes of order. That's really significant. All right. And so again, here's where that rule came in, the absolute 10 to the 2 difference. So we were able to drop off that plus 3x in the particular lanthanum 3-fluoride example because the amount of the common ion added was so large compared to the solubility or the the KSP at least value of that salt that it just made that 3x negligible. The last part you can read, but really it's not testable. It's just extra information for you. This concludes Lecture 4.